Okay, so that's our latest release of XFlow, 98/2016, and that's the standard view that you have once you open our software. Well, first of all, before going to the setup, I just wanted to quickly highlight three main regions of the GUI. We have on the left the project tree. That's where we do our setup, and as you can see, we have tabs which guide the user in setting up the simulation. We always work left to right, so we start from environment all the way to post-processing. And you can already see there is the same interface, which basically allows us to do setup, run, and post-processing. Then we have the graphic view, which is where we see our setup, and we can start, well, also adding geometries, and we're going to see some of the post-processing features of XFlow. And finally, we have the function viewer. It's where we plot everything these numerical functions, so forces, mass flow, probes, readings, and all of that is plotted in the function viewer. Okay. You do also have a message view, which we're going to see later on, tells you, well, of information on debugging on what's going on during the simulation run. Okay, so let's get started with the first demo, which is going to be the Petronas Tower. And although we're going to run it at a coarser resolution than the video I just showed you on the presentation. Okay, so let's start with the first thing first. So we go to environment, and that's our XFlow setup. By default, when we start, we have our wind tunnel, generic wind tunnel in XFlow, and that represents sort of equivalent of our experimental setup. So we have predefined boundary conditions on the sides, and the flow is supposed to come from -x and exiting the wind tunnel from +x. Okay. We also have predefined initialization of the domain, so everything is easier for the user to set up. Let's start modifying this setup. The first thing we're going to do is make it bigger. So it's just 12 meters, but we want to simulate the Petronas Tower. So we'll make it around 2 kilometers by 1 kilometers by 1.5. Okay, so now it's a little bit bigger, and what we will do is also center that on Y and move it a little bit downstream on X. Okay, we're going to see that once we import the geometry. Basically, we're going to have geometry closer to the -x axis. Okay, by default, we say we have condition that flow in from -x and gets out from +x, but we want to have a ground wall on the simulation, so we can switch this on. Okay, so now we have a wall represented in XFlow. Perfect. So let me leave this by default, and we come back later on those settings. If we go to materials, we're actually going to use standard air, so we're not going to change any of the settings. By default, XFlow is using a reference density of the air 288 Kelvin. Okay. And we start importing our geometry. Okay, so geometry tree is actually empty, so let's start with that. And I'm going to import my Petronas Tower geometry. And I got it. I just imported an NFB file, which is an XFlow format, but XFlow can read step files and ArcGIS files, which are parametric, but also STLs. Okay, and those are tessellated geometries. Okay. Let me change the color because I can't see much. So let's set it to a sort of a grayish. Okay, well, as you can see, we have the detailed geometry of our Petronas towers. We have a few of the elevators, I guess, there, or we have the bridge connected to. Okay, so we're going to use this full model to do our simulation. Okay, the only setup I'm going to change in here is the wall model we're using, which is the non-equilibrium enhanced. And this is particularly suited for external aerodynamics simulations, where the pressure gradients, adverse pressure gradients, are really important to capture correctly the separations of the flow field. Okay, perfect. So now we are all set on this. And let me go back to my environment. By default, we don't have any low velocity coming in, so I'm going to set a inlet velocity, and instead of setting a single constant velocity of 20 meters per second, I'm going to exploit XFlow capability of using functions. So I'm going to set a profile which is basically dependent on y. So there will be y plus 5 and divided by 10, so that's just a coefficient. And all of that is going to be power 0.154. Okay, so what I've done is actually input an analytical expression, and I can illustrate or show that in our function viewer. So we're going to have a value of roughly 18 at the wall, at the ground, at 0 meter, but then we're going to have an increase in velocity, okay, and then it's kind of stabilized after a few meters, of 50 or 60 meters. Okay, it represents a little bit the profile that the boundary layer can have, or an effect on the boundary layer of the wall. Okay. In addition to that, so we don't have a uniform inlet. We can actually simulate turbulence intensity. So the flow field that hits the tower is not going to be a clean flow field. It's going to be disturbed, so it's going to be turbulent, and we're going to set a turbulence generation model. Okay, by default that's off in XFlow, but we can set it to custom, and we can set up a turbulence generation model. Okay, the first parameter I'm going to set is the turbulence scale. So it's the characteristic scales that set up my turbulence in my simulation, and the second one is how I want to discretize the turbulence generation. The higher the number of harmonics, the more you actually discretize, the longer it will take to generate your initial turbulence field. Okay. You might actually see that now that we have turbulence generation, we have an inlet turbulence intensity as well on our low, so we can set a similar low of our velocity on the turbulence. Okay, so I can just copy paste that. But I'm going to modify that, and I'm going to change the exponent, that's 167, and let me add an additional graphic view. So we have, that's our velocity profile, and now I'm going to plot my turbulence profile, and as you can see is inversed. So we have a higher turbulence at the ground and a lower one as we go along with our y direction. Okay, so now we have our input condition set up. We could consider gravity if we want to by including our acceleration low on y, on minus y. Okay, as you can see, I can move around windows as I like when I'm doing the setup, and I'm going to simulate 30 seconds. So the actual characteristic of turbulence of these buildings are much slower than what we're used, at least to aerodynamics in aerospace, for example. So we need a longer time to simulate. I'm going to use an adaptive refinement, as we've seen in the video. So I'm going to specify a result scale of our far field, but then I can actually use my adaptive refinement to specify the resolution at the surface, so at the surface of the Petronas, but also the resolution of the wake, which is going to develop on the back of the Petronas towers. Okay, I'm going to add distance control, so I'm going to say, okay, refine my simulation in the wake up to 150 meters behind the geometry. Don't refine further than that. And the last thing I'm going to do is set a folder name for my simulation, set a frame frequency, which is telling me how many of my simulation time step I do want to save. So it's a different setting than my time step. So that's just for saving my information. And the time step is going to be automatically calculated by XFlow to give me a stable solution. Okay. And last but not least, I want some average field as well. So I'm going to have a transient simulation, but after 5 seconds, I'm going to start averaging my results. Okay, so at the end of the simulation, I can see an average field, which is the closest you get to a steady state simulation. Okay, perfect. I think we're all done. So environment is set, materials is good, geometry is done, and setup is clear. So we save that in our folder, and we call it Petronas Tower. Okay, and now that's basically our pre-processing, and in order to start it, we just hit the run start computation, and now we are actually starting the solver. It starts with creating the domain, so we are generating the lattice distribution, the discretization, and once that is done, which is already done, we have our solver, which is starting on the background. Okay, it does tell me a few information about my turbulence harmonics, my setting of the turbulence intensity. But what I'm going to do is just stop this simulation and I'll load the case that I did run previously so that we can do some quick processing. Okay, so that's the same simulation, exactly the same. You can see the number of elements of the simulation here on the top, and we do start with a lower number and then it starts increasing, so it's always changing during the simulation, and that's why it's an adaptive refinement. Okay. What I wanted to show is probably, yeah, we can show that one. So that's our average velocity field, and as you can see, well, it's much smoother than instantaneous. I'm going to show you an instantaneous in a while, but you can see, well, there is velocity hitting the tower, and we have the wake at the back, and some higher velocity go to the top. Okay, let me show you the very first frame, and let me put that to instantaneous. So now you can see the initial velocity field and the turbulence intensity that we just inputted in here, and that creates a sort of non-uniform velocity input. Okay, that is really important if you want to consider fluctuation on your average results, for example. Okay, so let me switch back to average, and now I'll show you some vectors. Okay, that's a similar plot, but now we're seeing the ground and we are visualizing vectors of velocity, colored by velocity. So you can see how the velocity well hits the tower, creates a few recirculation area here and there. For example, there's a big recirculation area in there. But you can start, well, moving the cutting plane around and raising it up, for example. And here you can see, well, not only there is well, a stagnation point there, but there's a sort of channeling effect of the two towers. So here the velocity is actually increasing because there is a decreasing in area. Okay. Whereas I can have a cutting plane actually crossing the two towers, so you can see the effect of the wake of one on the other. Still, you might remind that the flow is coming from X, so there is some effect, but it's not huge. If the wind were to come on from this direction, it would be a much bigger effect. Okay, and probably I wanted to show you some surface field. In this case, we are visualizing pressure on the surface of the tower. So we can see that there is a high pressure where the velocity hits, and then again low pressure at the back. Okay, perfect. I think that's basically it for the tower tutorial.